Talking about wave interactions. We talked about the sim and how it demonstrated reflecting at a fixed barrier and inverting, and reflecting at a free barrier to repeat just back along its original path. We then moved on to talking the law of reflection. Law of reflection indicated that the incident angle of a wave, regardless of what kind, was equal to the reflected angle of that wave. Okay? Yeah. Incident, yes. You'll also notice that pool balls actually obey the law of reflection when they bounce off objects. Yeah. Say again? Diamonds on the side. Oh, for targeting, yeah. Bad pool table, man, don't play on that. They like curve? That's weird. Throw that away. All right, types of mirrors. Aside from this flat mirror, we talked about concave mirrors, which were curved in. This is the one that looked like this, where we could focus on things. We then talked about convex mirrors, which bounce light out so it's scattered to everybody. Okay, so this is, not terribly brutal because everybody gets a little bit of the light. This one's all sorts of fun because I can definitely focus on individuals. And she's like, wait, blind me. Oh, I knew there was something I was supposed to do. I didn't fix the laser pointer. All right. After going you through both the convex and concave mirrors, we talked about their individual purposes. And then we moved on to refraction, which, where's my page for refraction? I don't know. We basically just launched into Snell's law, right? Oh, there it is. We talked standing waves first. We demoed some standing waves. We made some standing waves. Talked about nodes and antinodes. Talked about completely destructive interference, and that's what's used for noise-canceling headphones. Then we went on to refraction, being the changing of wave's direction due to a change in medium. And we had Snell's law, where we talked about the individual objects having specific wave speeds. Let me just move some stuff here. And we talked about it being used to identify gems. We talked about it being used to work with fiber optics, and what complete internal reflection was as we were trying to laser through the fiber optic cable. One piece that I need to add on here, where did I set all my pens? There we go. I have this set up equal to V2 over V1, but there's another term that we can use here when we talk about refraction, and that's an index of refraction. Index of refraction. An index of refraction is a ratio between the speed of light in a medium, or the speed of a wave in a medium, and the wave speed in a vacuum, or the speed of light in a vacuum. Index of refraction is N is equal to C over V, where N is the index of refraction. I'll go through it again, yep. C is speed of light in a vacuum. In a vacuum. And V is speed of light in the medium in question. So yesterday we shined, shines right? Whatever it is. A laser into the fish tank, right? We saw the laser bent. We saw that specifically in this one pretty clearly, correct? That means that the speed of light in the water is in fact different from the speed of light in air. We don't typically just state the speeds of light, or rather we state their indices of refraction, because stating the speed of light, this is 3 times 10 to the 8th meters per second. Okay, that's a really big number and it's unnecessary. Yes, that's in a vacuum. And this is the speed of light in the medium, which is probably going to be like 2 times 10 to the 8th meters per second. So we could really be working with much, much smaller numbers. So we could work with an example here, and actually let's just go ahead and calculate the speed of light and the index of refraction for, whoops, say that again. Yeah, index of refraction is the ratio of the speed of light in a vacuum to the speed of light in the medium. Yeah, it's basically a statement of the equation. Yeah. So let's go ahead and actually just run an example on this real quick. So if I've got my laser here, I want to walk around so I can actually see this. And I'm going to shine right there. It's coming in at a 65-degree angle. Okay, 65 degrees to the normal. It's exiting at, I'm going to go, that's about a 45-degree angle. So again, 45 degrees to the normal. So if theta 1 is equal to 65 degrees, this is air, and theta 2 is equal to 45 degrees, and this is water, we can use Snell's law to find the speed of light in water. Now, the speed of light in air versus the speed of light in a vacuum are incredibly close to each other. We're talking like 2.99 versus 2.98 times 10 to the 8th meters per second. So not really worth talking about in most cases. Okay. So using Snell's law, we found up here, we can say that the sine of 65 divided by the sine of 45 should be equal to V2 over V1, where V2 is the speed of light in air, so 3 times 10 to the 8th meters per second, over the speed of light in the vacuum, V. Okay, so I'm just going to go ahead and solve this. So sine of 65 divided by sine of 45, making sure that I'm in the right mode. I'm good. I get 1.28. I can then divide 3 times 10 to the 8th meters per second by that value and wind up with V. So 3 times second 10 to the 8th divided by that, I get 2.3 times 10 to the 8th meters per second. Speed of light in a vacuum or air.
So you use Snell's law?
I use Snell's law to determine this is the speed of light in water. Of light in water. So if I want to find the index of refraction, I would just take 3 times 10 to the 8th divided by 2.3 times 10 to the 8th, and I would show that that index of refraction, N for water, is 1.3-ish. Indices of refraction are unitless, so don't have to label it anything. Because they're calculated as speed over speed, so all the units cancel. Yeah, it's just a multiplier, yeah. All right, questions on indices of refraction, Snell's law.
What does an index
That
of refraction mean?
1.3 is a ratio of the speed of light in a vacuum to the speed of light in the substance. Basically, it's a factor of by how much is something going to slow down, which translates to a factor of by how much is something going to bend its path. Bend more. Yep. Indices of refraction are always higher than 1 because you can't go faster than the speed of light in a vacuum. Yeah. No. I'm going with no. Oh, okay. So questions on a prism. I can go ahead and tackle that here. So question was asked, how does a prism work? So when we say the speed of light is 3 times 10 to the 8th meters per second, really that's a generalization. Because technically the speed of light varies for every frequency, and therefore every color of light has a slightly different speed. And because every color of light has a slightly different speed, that means that they have a slightly different index of refraction and therefore bend at different ranges. So prisms work because each color of light has a slightly different speed and therefore a slightly different index of refraction.
So one color will get there.
Let me come back to that. Slightly different index of refraction. When they are in the non-vacuum, non-air medium, yes. So in a vacuum, they want to say they're effectively the same. Yeah, in a vacuum, they're the same. It's when they enter the new medium that the amount of energy that they're carrying varies, and they have different amounts of energy, and that different amount of energy changes the speed that they travel at when they enter that new medium. There, yeah, I said it right that time. In a vacuum, same speed. When entering the new medium, they have different energies. That different energy causes them to change their speeds at different rates. Speed, I can just put an annotation here because of their different energies, amounts of energy. So the ones with the highest energy would bend the least. So purple bends the least. The ones that would have the lowest energy, red, would bend the most. Red. All right. Let's see here. Refraction. Is there anything else up here that I need to say for refraction? Nope. I think we're good. Next up is diffraction. This is a new one. We didn't talk about this one yesterday. Diffraction is the bending of a wave as it passes a edge. Oh, God. Yeah, I'll cycle back to that. It's refraction. Just stop. All right, we'll just cover lenses right now. Too bad. All right, lenses. Thank you for reminding me. I was going to skip it. Okay, talking lenses. There are 2 different types of lenses we're going to cover. Those are convex and concave. Alternatively, you can call them converging and diverging. So I'm going to start with converging lenses. Converging is a concave. Or sorry, you had it right, convex. One that's shaped like this. Okay? When light or a wave, when light passes through a convex or converging lens, light bends so that it crosses at some point. That point will be called a focus. Eventually, we get the image to flip on the backside. So image flips. Image is magnified. Okay. This can be used for certain prescriptions of glasses and contacts. This is what your eye lens does, absolutely. Vertically.
Wait, so you get like glasses would take around 3 Does it flip it again?
So it depends on exactly how your prescription's set up. So typically this is going to be used if your eye focuses at a point further back. So it takes the waves, and your actual back of your eye would now be here. So it doesn't cause it to flip before it reaches your eye, because if the back of your eye were back here, you'd put on your glasses and you'd walk around and everything's upside down. No, your brain would not adjust to that. You would be walking around as though you were upside down all the time. It would be very disorienting. So if you take those kind of glasses off and hold them out, you'll see it flip. If you take off your glasses and you look, yeah, the focus would now be in front of you. But the focus is behind you when you put them back on.
No, it's not.
Nope, not his. I really don't know enough about the most common eye deformities to give you a good answer on that. Yeah, I guess I did. I mean, you could try, but they would say it was long before I came around. All right, the other one we've got are diverging or concave lenses. Okay, a diverging or concave lens is going to do the exact opposite. As light travels, a diverging or concave lens spreads out the light, and it does not focus. Okay, this causes the light to give you a wider field of view with less detail. It kind of is, yeah. Not flip. Provides wider field of view. And does not magnify the image. It's totally an eye. Not magnify. Yesterday, someone asked me about Galileo's telescope. Galileo's telescope would use these. There are a variety of different combinations that are used for refracting telescopes. The two major ones are the Galilean and the Keplerian telescope. So let's see here. If I remember it correctly, the top one here, and I should probably just look it up. Top one would be a Galilean, where the objective lens, meaning the first lens that light comes through, is a converging lens. So it takes a wider field of view, focuses it into a smaller zone, and then the diverging lens collimates that light so that we get something like this. So that we can take this larger piece and treat it as though our eye was that large, and our eye observes or takes in that much light. So not only does it magnify, but it provides additional clarity. A Keplerian telescope is way weirder. Kepler, I don't know why it's called a Keplerian, because he didn't actually use one. He didn't have lenses. Brahe and Kepler didn't use telescopes. He had something that had no lenses. Remember, it was iron sights, we'd said. What for Brahe? It was basically a giant protractor. Yeah, he used a giant protractor with a guide on it. These are not used for professional telescopes anymore because crafting a lens large enough for it to take in a good amount of light is absurdly difficult and expensive. So instead of trying to use refracting telescopes for astronomy or for anything reasonable, we use reflecting telescopes, which take a giant mirror and focus everything on one point. This is easier to make because you can form a giant mirror out of lots of small mirrors. You can't do that with a lens. You'd have refraction occur at every junction between pieces of a lens, whereas with a refracting telescope mirrors, it all just bounces back to one point. So these are cool for toys at this point. They're also useful for microscopes, but if you want something that's truly powerful and can see things far away, you need a mirror.
What is Hubble?
This is for microscopes. Big lens, or sorry, not lens, big mirror. The Hubble, actually, all professional telescopes are reflecting. Yep, we got a lot of them.
Could you use a better than a Hubble?
Oh, the Hubble sucks compared to what we've got. So we got our different kinds of lenses. We talked a little more telescopes. Now I get to go to diffraction. What? All right. As I mentioned earlier, diffraction is the bending of a wave as it passes an edge. The bending of a wave as it passes an edge. We can see this really easily with wave breaks in a harbor. So if you've ever been to any kind of harbor on the ocean, you'll notice that there's like rocks piled up along the bay. Their purpose there is to stop large waves as they're coming in, to create a more calm area where boats are actually stored. So if we've got our wave break, there's always a hole in the wave break so that boats can come in and out, and we've got waves out here. Our waves are traveling, our waves hit here. Without diffraction, waves here would stop, and we'd get waves that just come through here. And we'd get this narrow beam of waves. That's so not what we see. Okay? When the water wave hits that gap, it passes this edge here, and it bends around that. So instead, we wind up with waves creating arcs out from there. So they create basically a single source from which they propagate forward in all 180 degrees. We see that with more than just water waves. We can actually see that with light waves. I'm going to turn off the other two lights here real quick. All right, so grabbing your attention, bringing it back forward. So when we talk about the particles of a medium, regardless of whether it's a transverse or a longitudinal wave, the individual particles of a medium follow a trigonometric function in terms of their position. If we want to find the particle position, x, of any piece of a wave, that is simply going to be equal to, and I want to make sure this is not one I have memorized, a cosine 2 pi times the frequency times the amount of time that has passed. Now, you guys who are in calculus have probably seen one that's similar, where you've got x, a cosine, like omega t plus like phi or something. Okay, cool. Maybe you're getting there, because I know you get it by the end of the year. Calc. Okay, maybe just Birch taught it. Either way, 2 pi feet. All right, so an equation like this equation tells us where an object is with relation to its original position. So if we have a particle of a medium, such as a molecule of air, as a sound wave passes by it, that particle of air is going to move back and forth. A is the amplitude of its displacement, meaning how far does it move at its maximum displacement. So A is going to be amplitude. 2 pi, F is the frequency of that wave, and T is how much time has passed since the particle started moving. Okay, so if the particle starts at its rest position and then begins moving as a wave of certain frequency passes through it, we can find its position based on its amplitude here at time t. X is position, yes. T is time. That makes sense? No, never. What is the cosine of 0? 1. Cosine of 0 is 1, meaning that when we are talking about an object that is being displaced, we always talk about it having started from its maximum displacement. So t equals 0 at the particle's maximum displacement. Which is A, amplitude. Okay? So we do this because if you're a math person, you would have said plus some kind of phase shift here. Yeah, well, effectively, yes. And that phase shift would have allowed you to say, oh, I can start wherever I want. Physicists look at you and say, no, start where it's at its maximum and make the equation easier. Okay? It's cosine. So calculus students, if I wanted to know the velocity equation, what's it going to look like? So if I want to know the velocity of that particle, calculus students, I just take the derivative of the position function. Everybody else, this equation magically appears in front of you, and you can totally just use it. So I have 2 pi frequency amplitude, cosine, or sorry, not cosine, sine, you're right, 2 pi frequency time. No, because we're only taking it with regards to t. And these other ones do not relate with t. This here, yeah, that's a pi. Yep, it's still 2 pi. Yep. And if I wanted the acceleration, it's still the frequency. All right. For an individual particle in a wave, starting from its maximum displacement, x is the particle's position. We find x's position as the amplitude, its maximum displacement, times the cosine of 2 pi times the frequency times t. For the velocity of that same particle, still starting from its maximum position, we find its velocity to be negative 2 pi times the frequency times the amplitude, sine of 2 pi frequency times time. Lastly, the acceleration of the particle is negative 2 pi frequency quantity squared times the amplitude times cosine of 2 pi times the frequency times time.